So these notes are on gravitational potential energy and kinetic energy, PE and KE. And so we know that gravity is a force, and that force pulls everything down. We also know that work is equal to energy. And we know that work is equal to force times the distance. So if work is energy and force times distance is also work, then energy is equal to a force times a distance. So we start with the question, what has more potential energy? I have two boxes here. One box is 5 meters above the ground. The other box is 10 meters above the ground. If we know that work is energy and that work is force times a distance, then that work is going to be done on these two boxes. Which one has more energy? Well, it's the one that has the greater distance, or the 10 meters above the ground box. Which brings me to the idea that potential energy is force times the height. And so if force is a force, and that height, we've got this force of gravity is equal to mass times the acceleration due to gravity. And so if that mass times the acceleration due to gravity is our force of gravity, then we've got the potential energy due to gravity is mass times gravitational acceleration times the height, or the distance above the ground. So we can plug this into our 3-column worksheet, where we've got GPE, gravitational potential energy. The formula is PE equals mgh, where m is mass, g is the acceleration due to gravity, which is 9.8 meters per second squared, and h is the height above the ground. Our units, we have mass measured in kilograms, or kg. We have acceleration due to gravity measured in meters per second squared. We have height measured in meters. It is a distance above the ground. So we've got potential energy equal to kilograms times meters per second squared times meters, or that becomes kilograms times meters squared per second squared. And if you remember that from our unit on work, that is the same unit. So we have joules as our unit for work and as our unit for potential energy, because they are the same thing. We can plug this formula into our 3-column worksheet into our triangle. But our triangle has 3 values here in the bottom, m, g, and h. So it changes things up a little bit. Thankfully, we don't really have to solve for g, because g is always 9.8 on Earth. So we've got m, mass, is equal to PE over GH. That's this one right up here. We've got height, the height is PE over mg, which is this one right here. And we've got PE equal to mgh, which is right down here. If we did need to solve for g, we just cover it up, and we've got PE over m and h. That's this formula right there. Which brings me to kinetic energy. Kinetic energy is energy based on the motion of an object. And when this object is in motion, we see that it has a velocity. So everything that has motion has velocity. And so if it has velocity, it's got energy. Now, some objects might need more energy to get up to a certain velocity. Think a big truck versus a small car. To get to 70 miles an hour, a big truck is going to use a lot more energy. And so that means that kinetic energy is based on velocity as well as the mass of the object. So where does kinetic energy come from? Well, kinetic energy comes from other forms of energy. That's how we get movement, right? When we move, we have to turn energy into motion. And so other forms of energy are able to turn into kinetic energy. And here's an example. We've got a tennis ball. And if we were to throw a tennis ball into the air, we give it chemical energy from our motion, from our throw, from our food that we eat, and it turns into the motion of this object, of this tennis ball. And as it goes up, it's slowing down, so that kinetic energy is turning into potential energy because it's gaining height. So this potential energy is gained from the height. At the top of the throw, it's no longer moving up and down. It's got all potential energy, and then it starts to fall again. It's accelerating, so that acceleration is given by energy. That's potential energy that's being lost, kinetic energy that's being gained, and then at the bottom we've got all kinetic energy. So all that kinetic energy has been gained back. Now, sometimes we can't destroy energy or create energy, but we do get changing of forms. And so a good example of this is heat. Now, when energy changes forms from one to another, it goes into heat, and that's our final form of energy. So heat can never be turned into another type of energy completely. We can use heat to move water and things like that, create steam, which turns turbines, but the heat that's in that steam doesn't ever get turned into something else. And so what we end up seeing is that heat can never be reclaimed fully. And so a good example is a roller coaster. At the bottom of the first hill, there's friction loss of heat, right? There's friction of energy loss down there at the bottom of that first hill. And so the second hill on a roller coaster is never as high as the first hill. We'd have to add more energy if we wanted to get up higher. Now, some roller coasters have 2 lift hills, but most roller coasters only have the 1 lift hill that does that. So we've got conservation of energy here. Now let's look at our formula for kinetic energy. Kinetic energy is, remember, it's mass and velocity. So we have 1/2 the mass times the velocity squared, where m is mass and v is velocity. Our units, we have kilograms as mass, meters per second is our velocity, so we're multiplying that together. We've got kilograms times meters squared per second squared, right there. We know from our previous 2 formulas that those are measured in joules. We can plug this one into our triangle. Again, the triangle has 3 things in the bottom. It's a little bit different than our previous one. The 1/2 we don't really have to solve for, but we need to stick it in there anyway. So if we wanted to solve for kinetic energy, we say that it's 1/2 times mass times the velocity squared, or mv squared over 2 if you wanted to simplify that. We can find the mass. And the mass, we cover it up. We've got kinetic energy divided by 1/2 the velocity squared, kinetic energy over 1/2 the velocity squared. Or if we want to solve for velocity, we have to do 2 different things. We have to first of all isolate for velocity squared. So velocity squared is equal to ke over 1/2 m. That's what we've got right here. And then we square root both sides. And if we square root velocity squared, we get velocity. If we square root 1/2 m, we get square root of 2 ke over m. That's just a switch of the fraction there. 1/2 m turns into 2 ke over m. And that's just a little algebraic switch that I did. So that is our formula for kinetic energy. Once again, if you need to pause this and go back, you are free to do that. That's the purpose of these notes, and I hope you have a good day.